Here, we focus in on Jupiter and Saturn. As previously covered, the star system starts with part of a nebula, called a parent cloud, and a singularity. The part of our parent cloud related to Saturn, Titan, Jupiter, Io and Smithereens could have looked like this. Spiral in LL Pegasi shows an early parent vortex. The parent cloud turns into the parent vortex when the singularity becomes present. Vortex pathways slice the iron-dense clouds. Regions of dense iron atoms have too much inertia to follow the curve. Thus, each one flies out or exits from the vortex pathway it was in. Clues for the sequence of planet formation in a star system. 1. A planet's orbital inclination. Larger inclination goes with being earlier in the vortex flattening process. For example, Venus has an orbital inclination of 3.4 degrees. It exited the parent vortex when it was still thick. 2. Orbital eccentricity. The vortex pathway gets more circular over time and the flow of particles in the vortex speed up. 3. Tightness of vortex curve where the planet exits. 4. Size of the protoplanet's iron heart. Heavier iron hearts tend to exit earlier. 5. How the iron heart is oriented and spread out in the vortex pathway that it is in. This table shows some of these factors with most likely order of exit. We know that Jupiter was one of the first, because the direction of its magnetic field was not influenced by the external magnetic field of the vortex. Io most likely came from the same iron-dense cloud as Jupiter's core south. Saturn's orbital inclination is 2.5, but its magnetic field naturally aligned with the parent vortex. This lets us know that Saturn had some time in the vortex before exiting. When a protoplanet exits the vortex pathway, it starts to spin. From spin to induced electric field due to magnetic flux. From spin and induced electric field to molecules. From spin, induced electric field and molecules to compacted dense layers, discontinuity layers and heat. From changing electric and magnetic fields to planet's magnetosphere. This is an image that illustrates Jupiter's magnetic field lines. From burst of vapor from hot planet to ice shell. Space is very cold. From ice shell and cooling crust to atmosphere and ocean under the ice shell. In our solar system, planets formed as usual: Mercury, Venus, Mars, Io, Jupiter, Saturn, Uranus, and Neptune. Smithereens became a planet in the same lane as Io. And while it was still very hot, it crashed into Io. This caused an elastic collision, the killer crash. Consider the positions of these planets prior to the killer crash. As they start to crash, ice shells broke first, then the rocky bodies collided. The planets were still spinning. Most likely, this caused a big shock wave in the vortex. Io's path was perpendicular to that of ice and atmosphere. The force of impact was close to the ecliptic. Io lightly hit one of its moons, then rolled off and kept going. This moon is now known as Pluto. Jupiter's gravity attracted Io so that it fell into Jupiter from a long distance away. Jupiter's gravity and Io's velocity caused a low-angle impact crash into Jupiter. Debris splashed out in all directions. This debris then slid over a thin layer of water on top of smooth ice. Io, an object with mass equals 8.94 times 10 to the 25 kilograms, fell onto Jupiter, which has 2.53 times Earth's gravity, 24.79 meters per square second. Let the following watermelon drop experiment aid your imagination. In this video, the regular watermelon shows what happened to the majority of Io, it vaporized. The line X covered watermelon shows what happened to the inner hard part. It deformed, making cracks for volcanoes, and it kept traveling in its original trajectory.
Line X watermelon versus the road. That's insane. There's a watermelon from 45 meters up, bouncing on the road, and it's not breaking. I mean, you think of what a watermelon's normally made up of, it's gonna smash everywhere. But this product is just holding it all together, and it's actually got enough elasticity that it's just bouncing and coming back up. It's incredible. Oh, you're kidding me.
Is it broken inside?
Yeah,
it is.
It's definitely slushy. But
here we go.
oh,
it pretty much explodes.
Like, where has it gone?
Well, that's where it was.
I know, but like, as if you look around in every direction. This is the Linex watermelon that we dropped, and pretty much all around in the air is the other one we dropped.
It's like white. Is that just the sunlight on the water?
On the water.
Yeah.
It sort of looked like it just combusted. But this was like a big watermelon, and there's literally little fragments. Like I don't even know where it's all gone.
Causes sulfur to turn red. Heat from the crash turned sulfur red. This red sulfur gives the great red spot its color. The crash site on what is now Jupiter's moon Io, formerly Io. Let's call this crash the red crash. Wondering how an ice shell could survive such a crash? Ice is very strong to compressive forces. And Jupiter's ice layer is on the order of 2,000 kilometers thick. The kinetic energy of the red crash caused 1. Molecular dissociation, for example ammonia, NH3, into nitrogen and hydrogen. 2. Splash kinematics so that material went out in all directions from the crash site. 3. Heat energy that melted an unknown thickness of the ice shell to form a thin film of water. To the extent that we can consider the water layer on the surface of Jupiter's ice shell to be a thin film in 2 dimensions, then experimental work on the International Space Station provides some help with understanding how the gas material from the red crash formed the swirls we see today. Diffusion on thin water films in microgravity. First we see color particles inserted perpendicular to the surface. There is no movement without an external force. Then we see tracer particles inserted at an angle. Then we see what happens when heat is added. The red crash involved heat at the crash site.
Alpha Houston on space to ground 1 for Don. We're ready for your downlink.
Okay, I'm going to hit play.
I'm Don Pettit. I was fortunate enough to be science officer on Expedition 6 to the International Space Station. And during this expedition, we had several kinds of science that we did. We did programmatic science, which is well-planned and well-thought-out science, comes up from the ground and is orchestrated from the ground. And then we have science of opportunity. And this is science that is done at the discretion of the scientists on board space station. And this is kind of the discovery science. And during our mission, we called our science of opportunity Saturday morning science. So we've seen how you can make these films of water held in place with a wire loop. Now we're going to look at some of the things you can use these films for other scientific investigation. And since you have this sheet of water, fluid motion is basically eliminated perpendicular to the sheet. So it allows you to investigate motions and processes that occur within the plane of the sheet. So you basically have a two-dimensional problem that you can observe where motion in one direction has been eliminated. And we can observe the effects of forced convection and then the effects of diffusion. And so here we're going to look at some diffusion properties that the weightless environment of space station allows you to observe. And we have one of our standard 300 micron thick films that's 50 millimeters in diameter. We're putting drops of food coloring on the film. And notice that the food coloring just sits there. There's not any convection, which is causing this thing to get stirred around, unless you puff on it. And here we're puffing on it with a syringe with a little fine cannula tip. And while we puff on the film, you get fluid motion. But as soon as you quit puffing, the fluid motion stops.
So you can see how just the slightest amount of force from the air will make the water move, and if the water has pigment in it, why then the pigment will move, as you're seeing there. Houston Station on 2. I'm putting tracer particles in these, and these are white ones. They're white tracer particles. Going to put a couple drops of these in, and then get some convection going here, which stirs these particles around, and then wait for all the fluid motion to stop. So here we have a stationary pattern, and I'm taking the soldering iron that we have on space station, and I'm putting that tip close to the wire frame, and it adds a heat source, and that heat source changes the surface tension next to the wire, and the surface tension forces then get in a tug of war, and they incite this convection, the fluid motion that you are seeing here. And this is known as Marangoni convection. Now notice the direction of the convection here. It's going from the center of the film to the edge of the wire where the heat source is. And we will see something really neat here. It looks just like the other one, but it's significantly different. The last setups, the water film was slightly thicker in the center than at the edge of the wire. So the films were convex, and the fluid motion went from the center of the film to the edge of the wire. So here I have a film that is concaved, so it's thinner in the center and thicker at the edges. The convection is indeed reversed. So here we see an example of Marangoni convection where you have a convexed fluid surface and the fluid goes from the heat source away. When we had a convex surface, it went towards the heat source. Now watch this. This was a really interesting example. Look at the violent nature of that convection. And now we're going to actually touch the tip of the soldering iron to the fluid film itself. And again, look at the intensity of the convection that results from that.
The vectors of motion from the crash site resulted in flows on Jupiter's surface that go in opposite directions. Observe winds in opposite directions. Another, short, observation. Only about 10% of the outer gas layer at the equator has been examined. Lighter particles are on the outer surface of the gas layer. Heavier debris from the crash would be found fairly close to the ice shell at the equator. Image of Jupiter and Io. To turn to Saturn, we return to the site of the killer crash. The planets are objects with substantial mass. Pieces of debris from this crash were much lighter. 1. Splashes from Ilos and Smithereens' respective oceans. 2. Broken ice. The ice was made from elements that were characteristic in the vapors of Ilo and Smithereens, including water. 3. Fine rocky debris, possibly including nitrogen, sulfur, aluminum, magnesium, silicates, and organics. And 4. Gases from both Ilos and Smithereens' atmospheres. This debris was gravitationally attracted to Titan and Saturn. It could be that Titan gravitationally trapped methane from this lightweight cloud of debris. The gravity of Saturn and the velocity of the outward directed light debris provided the material that covers Saturn's ice shell and fills its rings. We can see through Saturn's ice shell to the atmosphere below at one pole or the other depending on the season. This light debris was primarily captured by Saturn, but some of it kept traveling and was captured by Uranus and Neptune. For each of these planets, observe the white ice shell under gas on the surface. In conclusion, both the proper model of planet formation and the repercussions of the killer crash are required to understand the features of Jupiter and Saturn. Allow this model of Jupiter and Saturn to compete with other models.